Hello, and welcome to my Lab1 video report where I investigate constant velocity motion using Newton's second law. In this experiment, I'm going to observe a ball moving at constant velocity in one direction. I will use a recorded video of an object in motion, extract position and time data, and then generate a computer model that best fits my observations. I will use Newton's second law as a basis of my model in predicting the future position and velocity of the ball moving at constant velocity. Newton's second law, also known as the momentum principle, states that the final velocity is equal to the initial velocity plus the sum of all the forces on the system divided by the mass of the system multiplied by a time interval delta t. In this experiment, I'll be estimating the velocity and position of the ball at intervals of delta t sufficiently close to, but not exactly equal to 0. The system is defined to be the blue ball moving at constant velocity. The surroundings are the floor and the air. The ball has been moving before it is in the camera's view to ensure constant velocity is being captured. My coordinate system for the experiment is set to be the origin on the far right. The ball's center is set to be on 0, 0, and it moves left on the negative x-axis. I could also move the coordinate system to be on the far left of the video, right about here. And I would acquire the same data. The only difference would be that the initial position would be a positive number, and the final position would be the origin 0, 0, but the velocity would still be the same. When I move the origin on the other side of the tracker, the slope remains the same, but the values are marked as positive values, and the graph approaches the origin at 0 I hat. But in the original system I've chosen the origin to be at the far right, and therefore the object moves from the origin towards the negative infinity. The graph at the right side of tracker shows the object's position with respect to time. The slope of the line, dr over dt, or delta r over delta t, is the velocity of the object. The mostly constant slope of the graph suggests that the ball was moving at constant velocity. This is the data I've obtained from tracker. The left side is the time and position data. The initial time and position of the ball is based on my choice of coordinate axes and can be obtained from the first entry of the data table. The next thing I computed was the initial velocity using the first two data points. Since the object was moving at constant velocity with 0 net force, using Newton's second law, I claim that the velocity will always remain constant throughout the entire duration, with the velocity being around about negative 1.38 I hat meters per second. To test this claim, I took the initial velocity, position, and time data from the tracker analysis. I used VPython to generate a graph of what the ball's position would be if the net force was indeed 0. I'll now compare this graph of ideal constant velocity versus the actual observed graph of constant velocity trackers produced to see how constant the ball's velocity really is. This is a graph of the two sets of data points plotted on the same plane. The x-axis of the graph is the time in seconds. The y-axis of the graph is the position based on my choice of coordinate axes in tracker. The blue line graph is the observed data taken from tracker, and the orange line with perfect slope is the data from VPython assuming ideal conditions of 0 net force. The two graphs line up almost perfectly for the most part until around about t is equal to 0.5 seconds. There, the observed velocity curve begins dipping below the ideal velocity curve predicted by the computer model. The computer model is an excellent approximation of the ball's actual position and velocity at varying times of t. However, it is not an exact fit of the data. Why is the computer model not a perfect fit for the data? Two possible explanations on why the model doesn't fit the observed data are friction and air resistance. Friction on the ground opposes the ball's direction of motion, and the air molecules also oppose the ball's direction of motion. These two combined cause a net force that is opposing the ball's direction of motion, which means that the net force is not actually zero. There are four forces that act on the system: normal force, gravitational force, frictional force, and air resistance. Normal force is the force that the ground pushes up on the system upwards, and gravitational force is the force that the Earth's gravity has towards the Earth's core. These two forces are equal, and therefore they cancel out to form a net force of zero. And assuming that frictional force and air resistance are zero, there is a total of zero net force on the system. This concludes my lab report. Thanks for watching.